Hello everyone, I'm Kai Yuedun, a PhD student from Nankai University. Here I'm giving a talk on the paper Improving Load Balance via Resource Exchange in Large-Scale Search Engines, and the authors are Kai Yuedun, Yusen Li, Trent Maibach, Gang Wang, Xiaoguang Liu. This figure shows a simplified architecture of a search engine. The raw documents are crawled from the internet and encoded into inverted index files. Large index files are divided and are used to construct multiple index shards. These shards run on leaf machines. The leaf machines are used for storing index files and processing a high rate of queries. When a user's query arrives at the search engine, it is dispatched to the shards. Then each shard performs a retrieval task on its index file. Afterward, a broker merges the partial ranked answer from the shards to produce a final query response. In order to improve resource utilization, multiple shards are usually placed on each machine and share the resource. The load rebalancing problem may occur when multiple shards are arbitrarily placed on machines or new leaf machine join the search engine. To handle the load rebalancing problem, some search engines, for example the Elasticsearch, try to reassign shards among machines. The previous work has theoretically proved that the class of load rebalance problem is NP-hard. Since the search engine service must not be interrupted during the reassignment, generally the procedures of reassigning a shard as follows. First, a copy of the shard is constructed on the target machine. Next, the query requests are redirected from the original shard to the newly constructed shard. Finally, the original shard is destroyed and the consumed resource on the initial machine are released. During the shard reassignment, some resources, for example DRAM or disk space, are consumed simultaneously by the shard on its initial machine and its copy on the target machine. We call such resources as transition resources. Transition resources affect the shard reassignment. For example, in this graph, machine M1 and M2 have identical capacities for the transition resources, and the resource demands of shard S1 through S4 is normalized to the capacity of a machine, and they are marked by the percentages. We simply assume that the load of a machine is the sum of the shard's resource demand on that machine. Based on the above assumption, obviously M1 has more load than M2. If we can swap S2 and S4, then the load of M1 and M2 will be balanced. However, we cannot make it because the remaining capacity of transition resource on M1 is insufficient. In this paper, we propose to use the exchangeable machines for facilitating the shard reassignment. The exchangeable machines are vacant, which means they do not have any shard initially. Moreover, if we use exchangeable machines, then after the shard reassignment, we are required to return some vacant machine as compensation for using them. This figure displays a toy example of using exchangeable machines during the shard reassignment. Note that we use assumptions described in the previous slide. Suppose we have an exchangeable machine M3, which has the same capacity as machine M1 and M2. Because there is no shard placed on M3 initially, and the transition resource capacity is sufficient for reassign shard S1 and S4 to M3. Next, we reassign S2 to M2 for making M1 vacant. That is the compensation for using M3. Now, both M2 and M3 are load balanced, and M1 is returned. We formulate the shard reassignment problem as an integer programming model, where we are given a set of leaf machines, a set of shards, and a set of exchangeable machines. The resource considered in this paper is abstract and virtualized. Initially, each shard is assigned to a leaf machine, and thus all the leaf machines are not initially vacant. Our objective is to generate a shard reassignment plan within a given time limit, for example 10 minutes, and this plan minimizes the load imbalance by reassigning shards among machines. Note that after the initial assignment, the consumed capacity for transition resource on each machine will not be restored before the given time limit expires. And actually, we do not physically move the shards. We list a part of notation and formula in this slide. The objective function is to minimize the global imbalance. Specifically, It aims to minimize the difference between the resource utilization of unweakened machines and the expected utilization. And the expected utilization is a fraction. It treats all leaf machines as one huge machine, and at the same time, it treats all shards as one huge shard, and calculates the value of the resource demand of the huge shard divided by the capacity of the huge machine. The reassignment should obey a set of constraints. The first one is a single principal constraint, which means that each shard is allocated to one machine. The second one is a capacity constraint, which means that the total consumption of each resource on any machine cannot exceed the machine's capacity. The third one is a transition constraint, which means that there should be enough transition resource capacity for a shard on its initial machine and target machine to meet its demand. The fourth one is conflict constraint, which means that for parallel processing and fault tolerance, each index shard has multiple replicas, and multiple replicas of one shard are not allowed to run on the same machine. The fifth one is a quota constraint, which means that we are required to return weakened machines as a compensation for using exchangeable machines. Specifically, since machines are heterogeneous in a data center, we need to ensure that for each resource, the sum of all the weakened machines' capacity after the reassignment is at least the sum of all exchangeable machines' capacity before the reassignment. Again, we also need to ensure that each returned machine should be weakened. Since the rebalance problem is NP hard, and the problem scale is generally large for search engine data centers, it is not plausible to find optimal solution using exact algorithms within a given time limit. Therefore, we design a heuristic algorithm called SRA to approximate the optimal solution. The SRA has two main steps. The first step aims to quickly reduce the global imbalance by reassigning shards from top K machines with heaviest workload to the other leaf machines. And to this end, we perform a linear search in this step. For the second step, we iteratively improve the solution by using a large neighborhood search, that is the LNS. In the second step, we create as many subproblems as possible, and we apply an integer programming optimizer to solve each subproblem. We only accept each subproblem's solution that can reduce the current imbalance, and further update our current reassignment plan based on the accepted solution. Furthermore, we adopt the linear search and the local search to handle the subproblems where the optimizer fails to produce a good solution. Again, our reassignments are theoretically simulated rather than physically operated. The second step also contains two substeps. The first substep is in the blue dashed box, while the second one is in the red dashed box. In the first substep, we reassign shards among leaf machines only. We create a subproblem by randomly selecting a subset of leaf machines together with all the shards on those machines. Next, we check if the global imbalance is stable in the last p iterations. If so, we move to the second substep, where we consider using exchangeable machines. However, using exchangeable machines will increase the problem complexity, so it's very critical to determine when the exchangeable machines should be considered. In our design, the criterion of using them is that global imbalance cannot be reduced for a fixed number of iterations in a row. In the second substep, by default, no exchangeable machine will be used. Thus, the boolean variable flag is set to false and the failure counter t is set to 0. Next, we create and solve a subproblem, update the counter t based on the result if the global imbalance is decreased. If the counter t exceeds a threshold, then we deduce that the current setting cannot efficiently reduce global imbalance in succession. Thus, we reverse the value of the boolean variable and reset the failure counter. If the number of machines in unsuccessful subproblem exceed a threshold k, then we apply the linear search and the local search to find a possible better reassignment plan for those machines. Again, we also check the running time in second substep. We evaluate the performance of our method using both synthetic dataset and real dataset from Baidu, which is the largest commercial search engine in China. We simulate 8 classes of input settings. They are C1 through C8. For this synthetic dataset, the R1 denotes a normal resource and the R2 denotes a transition resource. For C1 to C4, they all contain homogeneous machines, which all have the identical capacities for resource R1 and R2. For C5 to C8, they all have heterogeneous machine, which means the capacities of each machine for resource R1 and R2 are different. The uppercase letter L and S represent the resource demand of a shard, and the former means the demand is large, while the latter means small. A larger alpha resulting in fewer shards on each machine, whereby the volume of shards is well below capacity. A larger beta, which is not listed in the slide, resulting in a large variance in the number of shards on each machine, whereby workloads are more imbalanced. In regards to the real dataset, the machine's capacities and shards demands are normalized together into an interval from non-inclusive 0 up to an inclusive 1. In this experiment, we use synthetic datasets under different alpha and beta parameters to simulate 1,000 leaf machines and 100 exchangeable machines. This figure plots the global imbalance produced by 3 algorithms. They are SRA without using exchangeable machines, denoted by SRA no EX, and SRA and a noisy local search, aka NLS, which is a cutting-edge algorithm used for machine reassignment problem. The percentage displayed in this figure indicates the proportional improvement of SRA over the NLS in terms of the global imbalance. We have several observations. First, the SRA and SRA no EX significantly outperform NLS for most of the input settings, indicating that our heuristics are more effective than NLS for reducing global imbalance. Moreover, SRA performs best for all the input settings, substantiating the effectiveness of using exchangeable machines. Second, the SRA outperforms NLS at input setting with both high and low alpha parameters, indicating that SRA is effective for both low and high machine utilization scenario. Third, the global imbalance produced by each algorithm for the heterogeneous machines is much higher than that for the homogeneous machines, implying that the reassigned shards among heterogeneous machines is more difficult. More observations and analysis are described in the paper. We evaluated the performance of the algorithms for real datasets. The figure plots the global imbalance produced by each algorithm. The proportion of exchangeable machines is 5% of the number of leaf machines. We observe that the global imbalance produced by 3 algorithms is much higher in dataset DS3 compared with other datasets. There are 2 reasons that may explain the finding. First, the DS3 is similar in problem size to DS1 and DS4, but its machine's utilization is higher, which indicates that there is less room for accommodating shards reassigned from other machines, increasing the difficulty of shard reassignment. And second, the DS2 and DS3 have similar machines utilization, but DS3 has a larger problem size, and thus the problem complexity of DS3 is higher than DS2. Therefore, reassigning shards in DS3 is more challenging, so the total global imbalance is high. More observations and analysis are described in the paper. We next analyze how the running time affects the performance of each algorithm. In this experiment, we simulate 1,000 leaf machines and 100 exchangeable machines. We test 6 various time limits, from 10 minutes to 1 hour. We set alpha to 0.2 and beta to 0.1. This figure plots the global imbalance produced by each algorithm under various time limits. As can be seen that the global imbalance decreases as running time increases for all the algorithms. Obviously, there are more reassignment operations as we extend the running time. Furthermore, when the time limit is small, for example, less than 30 minutes, the SRA outperforms NLS significantly, indicating that the SRA decreases the global imbalance efficiently. As the time limit grows over 30 minutes, the benefit of SRA over NLS becomes less significant because all the algorithms converge to a good solution and the global imbalance is close to the optima. The figure on the left side plots the global imbalance provided by SRA when providing various quantities of exchangeable machines. In this experiment, we use a synthetic dataset and simulate 1000 leaf machines, and set alpha to 0.2 and beta to 0. We change the number of exchangeable machines from a proportion of 1% to 10% of the number of leaf machines. So there will be 10 to 100 exchangeable machines. There are two observations. First, the global imbalance for the heterogeneous settings, that is C5 to C8, is greater than the counterpart for the homogeneous settings, that is C1 to C4, which confirms that balancing workload among heterogeneous machines is more difficult. Second, using more exchangeable machines will not always succeed in decreasing the global imbalance. For example, in input setting C1, the lowest global imbalance is achieved when we providing exchangeable machines at the proportion of 3%. Intuitively, more exchangeable machines should provide more room for reassigned shards, producing a lower global imbalance. However, providing more exchangeable machines increases the size and complexity of the problem to be solved within a short time. The figure on the right side also plots the results of using various quantities of exchangeable machines, but this time we focus on the real dataset. The number of exchangeable machines is also set to a proportion of 1% to 10% of the number of leaf machines. We observe that there is a clear downward trend in global imbalance of DS3, which indicates that using exchangeable machines facilitates reassigning shards in DS3. We also observe that using more exchangeable machines can now reduce global imbalance further, especially in DS2. The reason is just mentioned based on the result from both synthetic dataset and real dataset. The number of exchangeable machines should be at most 5% of the number of leaf machines. To test the scalability of the three algorithms, we simulate 1000, 2000, and 5000 leaf machines based on the input settings C1 and C5, because they have far more shards than others. We set alpha to 0.2 and beta to 0.1. The number of exchangeable machines is 5% of the number of leaf machines. The results are reported in this figure. We observe that the global imbalance produced by each algorithm grows as the size of problem increases. This is reasonable because reassigning shards in a large problem scale is more challenging, as we have illustrated earlier. For all problem scales, the SRA outperforms both SRA NoEX and NLS significantly, which indicates that SRA is still effective for large problem scales. In order to compare the SRA with the optimal solution, we derive a lower bound through a branch and bound approach on a relaxed model, which means we temporarily ignore all the integrity restriction in the original model. More details are described in the paper. In the experiment, we consider a small problem scale due to the NP hardness, where we simulate 100 leaf machines and 5 exchangeable machines. We set alpha to 0.2 and beta to 0. We use Groovy to implement the branch and bound approach and obtain the lower bound by running the software for 12 hours. This figure presents the global imbalance produced by each algorithm against the lower bound for input setting C5 through C8. Note that the percentages in the figure indicate the performance difference between the global imbalance achieved by SRA and the found lower bound. Marked by relaxation, it can be seen that the performance of SRA is close to the lower bound. The gap is 18% on average, substantiating the effectiveness of SRA. In this paper, we study a new shard reassignment problem for improving load balance in resource-stringent search engines. We propose a mechanism of using exchangeable machines and design the SRA to handle the proposed problem. The experimental results demonstrate the utility of using exchangeable machines with an average reduction in load imbalance of 58% versus NLS on synthetic dataset and 25% on real dataset. Moreover, there are two trade-offs in solving the proposed problem. The first one is the advantage of using exchangeable machines and the side effect such as increasing the problem size and complexity when we apply for excessive exchangeable machines. And the second one is the reassignment plan should be generated as soon as possible. And on the other hand, we have to ensure the solution quality of the plan. We do not deploy the SRA on a real data center. Some experiments, for example, reducing query processing time, cannot be measured. Thank you for watching this video.